Hello there, and welcome back. In this video, we're going to be introducing a piece of analytical machinery that is really useful for dealing with distributions either that you're familiar with, trying to build, trying to analyze, or trying to approximate. And these tools are called moment generating functions, or in short, MGFs. So let's just briefly describe a problem that will motivate the creation of such tools. So let's suppose that x is some random variable. It doesn't really matter which random variable, discrete or continuous, bounded or unbounded. And let's just use a common example, such as the binomial random variable. So if x is a binomial random variable, then what do we know about it? So we should know the distribution for it, so the PMF. So we know that the PMF for a binomial distribution is going to be C and choose x. 1 minus p to the n minus x times p to the power of x. So what is the expected value of a binomial random variable? Well, if we don't know the formula for it, we can always use the definition of expected value for a generic discrete random variable. So that's just going to be the sum from x is equal to 0 to the power of n, or to the upper limit of n, of x times the probability mass function. So that's going to be equal to n factorial x factorial times m minus x the quantity factorial times 1 minus p to the n minus x times p to the power of x. And if you're not comfortable with math, or maybe you don't like math, or even if you're good at math, being able to evaluate the sum may be tricky, or analytically impossible to you if you don't have the appropriate tools for it. But of course, you can evaluate this. I believe I went through the proof of it and when I actually introduced this particular distribution. But one can show that this is equal to n times p. It's a very simple thing that it simplifies to. But generally speaking, this process can sometimes be difficult. Sometimes it's easy. Look at the uniform distribution. It's not super difficult. But it can sometimes be difficult to find directly using this approach, at least. So this then brings us to an important question, because the mean and the standard deviation and possibly the skewness and kurtosis of random variables are very useful in sort of describing what the distribution is doing over some period of time. So is there a nice way to generate all, not just the expected value, not just the second moment or the variance, not just the skewness or kurtosis, but all moments of a random variable, provided that they exist? Now, what do I mean by provided that they exist? Like, is it possible that the mean or the standard deviation or the skewness of a random variable not exist? The answer is especially yes. But I'm not going to get into that discussion, especially now. That's more of a intermediate to advanced topic for the probability theory. So we'll just investigate that later once we get to it. But for now, let's assume that these do exist. And if they do exist, how are we going to find them in a nice, very straightforward way, regardless if it's discrete or continuous, right? So if you took Calculus 1 or maybe even an advanced pre-calculus class, you should know that the function e to the power of x can be represented as an infinite sum. In particular, the sum from k is equal to 0 to infinity of x to the power of k all over k factorial. And if you've never seen this sum before, then you can sort of take this as a definition for this particular function e to the x. And what does that mean? So if you want to find e squared, 2.718281828 to the power of 2, how could you approximate that? So you can do x to the 0, which is 1, plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial, and that can serve as an approximation. If you want a more accurate approximation, you can just include more terms of this infinite series, right? So that's just the function e to the power of x. Now what I'm going to do is I'm going to replace this number x with the random variable x. So we're going to let x be a random variable. So if that's the case, that means e to the random variable x is going to be equal to 1 plus the random variable x plus the random variable x squared over 2 factorial plus the random variable x cubed over 3 factorial plus the random variable x4 over 4 factorial all the way outwards. So notice, if we were to introduce an expected value into this relationship, notice that this would give me the expected value of x, this would give me the second moment of x, the third moment of x, the fourth moment of x, and so on. So technically, all of the moments of a random variable x are in this expression where e to the x gives us a relation between all of them. So this expression relates all moments of a random variable. Now I might want to include another word here, all integer or positive integer moments, because some people might want to consider, what about the half moment of a random variable or a third moment or the pith moment of a random variable? Now what do those even mean? Definitely not the discussion or purpose here, but maybe you want to sort of think about that if you're considering studying maybe fractional calculus or something like that. So with this observation, this then motivates the creation of what we call a moment generating function. So let's define what that is. So the moment generating function of the random variable x is going to be defined by mx, so the moment generating function for random variable x, and it's going to be of some parameter t, and it's going to be equal to the expected value of the random variable e to the t capital X, where t is just some parameter, which we'll discuss momentarily. So this is the definition of a moment generating function for a random variable x, regardless if it's discrete or continuous. So x could be Poisson, binomial, hypergeometric, log normal, normal, exponential, continuous, uniform, it doesn't really matter. Well, how do I find the moment generating function for a random variable, and what properties would it have? So what is e to the tx? So e to the tx is just going to be equal to the sum from k is equal to 0 to infinity of t capital X to the power square k all over k factorial. And then I can distribute my expected value over my sum, and I can give you some idea of what that's going to be equal to. So that's going to be equal to the expected value of 1 plus the expected value of tx plus the expected value of t squared x squared over 2 factorial plus the expected value of t cubed x cubed over 3 factorial plus and so on. So if I treat t as a constant and t squared as a constant and t to the n as a constant, I can, as we're going to eventually show, can be factored out of the expected value operator. So therefore, the moment generating function for a random variable x of parameter t is just going to be equal to, and one can also show that the expected value of a constant is just itself. So we're just going to have 1 plus t times the first moment of x plus t squared over 2 factorial times the second moment of x plus t cubed over 3 factorial times the third moment of x, and so on. So we get this expression. Now, let us assume that you know calculus now, and let us just take the derivative of this expression with respect to t. So what is the derivative with respect to t of this particular function? So if I take the derivative of a constant, I should get 0. Keep in mind the expected value is just a number, so the derivative of a number times t is just going to be that number. Nextly, the expected value of x squared is just a number, and the derivative of t squared over 2 factorial is just going to be equal to t, so we're just going to have t times the second moment of x, and then the derivative of t cubed over 3 factorial is just going to be equal to t squared over 2 factorial times the third moment of x, and then we're going to have out here t cubed over 3 factorial times the fourth moment of x, and so on. So what am I going to do here? Keep in mind that t is a real number. So what I can do is choose t to be equal to 0, right? So if I choose t to be equal to 0, this is going to go to 0, this is going to go to 0, that's going to go to 0, and I'm just going to be left with e to the expected value of x. So that means the derivative of my moment generating function evaluated at t is equal to 0. And there's a nice way to just represent this. This is just mx prime of 0, right? So if you're in Desmos, you're just going to prime the moment generating function evaluated at 0, and this is going to give you the first moment. And keep in mind, this random variable is arbitrary, so it doesn't really matter what the variable is, but the first derivative of the moment generating function evaluated at 0 always is going to be the first moment. Similarly, one can also show that the second derivative evaluated at 0 is going to be equal to the second moment of the random variable. And you can generalize this to any natural number n. Therefore, we get the very beautiful property that the nth derivative of the moment generating function of a random variable x evaluated at 0 is always equal to the nth moment of that random variable. So therefore, if you know the moment generating function, you can find practically any moment you want just by finding the nth derivative and evaluating it at 0. So up to this point, what do we know about moment generating functions? Well, we know the definition. The moment generating function for a random variable x of parameter t is defined to be equal to the expected value of the random variable e to the t capital X. So what consequences does this definition give us? Well, one can show that the moment generating function evaluated as 0, so the 0th derivative of the moment generating function, is just going to give us the constant that's hanging out in the front of that infinite series. And more importantly, of what we just realized, is that the nth derivative of this moment generating function, evaluated as 0, is always going to give us the nth moment of that random variable, right? So that's the most important part. But technically, every moment generating function is going to have this property, provided that the moments exist and hence the derivatives exist. Now, more importantly, these are important properties, of course, but how do we find the actual function mx of t, right? So up to this point, we just know some properties that this function will have and some of the things that it can give us. But how do we actually find what this function actually looks like, right? So if we just look at mx of t, so by definition, this is just going to be the expected value of this random variable. So if we use the definition of the expected value of a random variable, which that definitely is, that's just going to be equal to the sum across all values in the support of that random variable of e to the tx times that probability function pxx. If it's discrete, and if it's continuous, that's just going to be the integral over the support of our random variable of etx times our probability density function for a random variable. And that's going to be what we're going to do if it is continuous, right? So we have two directions for which this can go, which of course varies depending on whether it's discrete or continuous. So let's just do an example of each, discrete and continuous, and see how we would actually generate the moment generating function of some particular random variables that we've already been exposed to. Right? So let's start off with a very easy one, in particular the Poisson random variable, which is a discrete random variable, right? So we already know that the probability mass function for a Poisson random variable is e to the minus lambda times lambda to the x all over x factorial. And remember that the support of this random variable is 0, 1, 2, 3, up to positive infinity. So we know the expected value and the variance are both equal to lambda, but what if we want to calculate, for example, the skewness or the kurtosis or any other moment and any other linear combination of all of the moments of this particular random variable? How would we easily generate the formulas for all of them very rapidly? Or if we have software, we can always use Desmos to approximate the derivative at 0 for each of these derivatives of this MGF, and then we can get the answers at least in approximate form. So what do we know? So the moment generating function for a Poisson random variable is going to be equal to the sum from x is equal to 0 to positive infinity, so that's our support, of e to the tx times e to the minus lambda, lambda to the x, all over x factorial. So let's just do a quick little proof of how we would go about this if we're a little bit clever with some mathematics. So that's just a constant, so we can always factor that out. So we're going to have e to the minus lambda times the sum from x is equal to 0 up to positive infinity. What else do we know? So we have a power of x in terms of those two things, so maybe we can group them together, and indeed we can. So that's going to be equal to lambda e to the t all to the power of x all over x factorial. So I'm just going to use a u substitution here. I'm going to let u be equal to that inside, so lambda e to the t. So this is just going to come out to e to the minus lambda times the sum from x is equal to 0 to infinity of u to the x all over x factorial. So this expression should look very familiar to you, at least if you've been paying attention so far. That's just the definition of e to the u, right? So this is just going to be equal to e to the minus lambda times e to the u, where u is equal to lambda e to the t, right? So this is the moment generating function for a Poisson random variable. Keep that in mind. So let's just fill in the details because we didn't start off with this u, right? So that's just going to be equal to e to the minus lambda times e to the lambda e to the t, which is just going to be equal to e to the lambda e to the t minus lambda, and we can factor out a lambda out of that top expression, right? So we're going to have e to the t minus 1 times lambda in the exponent of e, right? So therefore, if x is Poisson, then the moment generating function for this Poisson random variable is going to be equal to e to the lambda e to the t minus 1. So that is the moment generating function for a Poisson random variable. Okay, so let us assume we want to calculate the first, second, third, or fourth moments of this random variable by using this moment generating function, right? So we would first find the derivative of this moment generating function with respect to t. So we just want to find the derivative with respect to t of e to the lambda e to the t minus 1, and then evaluate this at 0, right? So in Desmos, you would just be like, mx prime 0 is equal to something, right? So let's just do this by hand, a little calculus review. So this is just going to be a chain rule. So this is going to be equal to lambda e to the t times e to the lambda e to the t minus 1 times, that's it, right? So that's going to be our chain rule. So that is our derivative of our moment generating function. Now I'm just going to evaluate this at 0. So we already should know what the first moment of a random variable for a Poisson is. It should just give us lambda, right? So what do we see? So mx prime 0 is going to be lambda e to the 0 times e to the lambda e to the 0 minus 1. E to the 0 is 1, minus 1 is 0. 0 times lambda is 0. E to the 0 is 1. Then that's equal to 1, and then we're just equal to lambda. Therefore, the expected value of a Poisson random variable is equal to lambda. What about the second moment? So we can continue in this fashion. So the second derivative of the moment generating function is just going to be the derivative of the first moment, right? Or the derivative of the MGF. So we just need to find the derivative of that answer that we got before, right? So e to the t minus 1. Now, if you want to skip all of the steps, technically you can just be like, okay, if I want the second moment of the random variable, I'm just going to find the second derivative and evaluate it at 0 and figure out what that is, right? So let's just go through that just in case you do know some calculus review. So we're just going to be using a product rule, so this times this. So first, times the derivative of the second, right? So e to the t minus 1 times lambda e to the t, and then plus the second times the derivative of the first. So that's going to be lambda e to the t. Right? So that is the second derivative of the moment generating function with respect to t. And now what I'm going to do is I'm going to evaluate this at 0. So m double prime x of 0 is going to be equal to lambda. So e to the 0 is going to be 1. And then we're going to have, that's 1 minus 1 is 0. So that's going to be equal to 1. And then that's going to be equal to 1. So we're going to have a lambda chilling there. then plus e to the, so that's going to be 1 minus 1 is 0, so that's going to be 1. Let's just write 1 there, not e to the 0 because we already know what it is. Then we're going to have a lambda there, and e to the 0 is going to be 1. So we have lambda squared plus lambda, right? So what is this? This is the second moment of a Poisson random variable. So what do we know? So that means the variance of this random variable is going to be equal to the second moment minus the first moment squared, and as you see, those lambda squareds cancel, and we're just left with lambda. So as we already know, the expected value and variance of a Poisson random variable are both equal to lambda, and we can of course justify that sigma x is going to be equal to the square root of lambda, whatever that number is. Right? Now we could continue this process onwards into the third moment, right? So the third moment of this random variable that is Poisson can just be found by doing the third derivative of the moment generating function and evaluating it at 0. And of course, if you want the fourth moment of this Poisson random variable, you would just do the fourth derivative of x, evaluated at 0. And also keep in mind that some people will abbreviate that by m4x evaluated at 0, right? But that's pretty much what you can do, and you can continue this as many moments as you want to generate. So that's how you would do it for a discrete random variable. Now let us take a look at the continuous case. So for our continuous case, let us assume that x is an exponential random variable. So what is the probability density function for a exponential random variable? So know its PDF as f of x is equal to lambda e to the minus lambda x, where lambda is some rate parameter. And also keep in mind that the domain of an exponential random variable is 0 to infinity. So how do we find the moment generating function for an exponential RV? So we would just go about it in the same exact way, same exact definition. So the moment generating function for this is going to be equal to the expected value of the random variable e to the tx. Now, since we're working in the continuous world, the expected value is going to be an integral over this domain of definition. So this is going to be equal to the integral from 0 to infinity of e to the tx times our PDF, lambda e to the minus lambda x dx. Right? So let's just play around with this expression and see what this is going to come out to. So this is a constant which can definitely be factored out. So this is going to be equal to lambda times the integral from 0 to infinity. And we can also combine these exponential expressions since they're the same exact base. So that's going to be equal to e to the t minus lambda to the power of x dx. Now keep this in mind that this curve, this integral only converges if this is an exponential decay curve, right? So the only way that the area underneath this curve is bounded, because we need to go from 0 to infinity, right? So the only way that this is going to get close to some number is if this is a decay curve. If it was an exponential increasing curve, this integral would go to infinity and hence not exist. So the only way that this integral converges is if lambda is bigger than t. Because if lambda is bigger than t, that means t minus lambda is going to be a negative number. That's going to give us a negative coefficient in front of x, which is an exponential decay curve, which definitely converges, right? So let's assume that lambda is bigger than t, and that's actually not going to be a harsh assumption as well, right? So, because remember, when we evaluate our moment generating functions derivatives, remember we're going to be evaluating at t is equal to 0. And lambda is always a positive rate parameter anyway, so all will be good on that front. So therefore, this restriction isn't going to really hurt us that much. So let's just do some baby calculus here. So that's going to give us lambda times t minus lambda is going to be a constant. I'm going to be dividing by it. And then we're going to be evaluating t minus lambda to the x, evaluated as x goes to infinity and as x goes to 0. So in the front we have lambda over t minus lambda. As x goes to infinity, this curve goes to 0 by assumption, and as x goes to 0, this goes to 1. So 0 minus 1 is equal to negative 1, and hence I can reverse my direction of subtraction in the denominator. Therefore, my moment generating function for an exponential random variable is going to be lambda all over lambda minus t. So that's my MGF for an exponential random variable, and then I can prove all of my formulas for my exponential random variable. right? So how would I find the expected value of an exponential random variable? I would first find the derivative of my MGF and then evaluate that at t is equal to 0. So I need to find, well, what is the derivative of lambda all over lambda minus t? And then I need to evaluate that at t is equal to 0. So using our quotient rule or maybe an inverse power rule, one can find that that's just going to be equal to lambda all over lambda minus t, the quantity squared, and then we need to evaluate this at t is equal to 0. So when t is equal to 0, we're just going to have lambda all over lambda squared, which is 1 over lambda, which we already know is the formula for the exponential random variable expected value. Now what about the second moment? So how do we go about that? So the second moment of an exponential random variable is just going to be equal to the derivative of the moment generating function evaluated at 0, and one can find that that's going to come out to, once you do the calculus, 2 all over lambda squared. So if you go through that process, how would you find the variance? So the variance is going to be equal to the second moment minus the mean squared. So we're just going to be left with 2 minus 1 all over lambda squared, which is 1 over lambda squared, which we already know, and thus proving that sigma x is equal to 1 over lambda, the same as the expected value for an exponential continuous RV. Now, for you more advanced math people, you might be able to use mathematical induction to prove a very useful identity via this approach, that the nth moment of an exponential random variable is actually just equal to n factorial all over lambda to the power of m. So generating the formula for skewness and kurtosis and all of the other moments for exponential RVs are actually pretty easy, because this is a nice, beautiful closed form for that. Right, so now let us just mention another random variable that we definitely have studied a lot about. For example, let us suppose that x is a standard normal random variable, right? So if x is a standard normal random variable, then we know that its probability density function is 1 over the square root of 2 pi e to the minus 1/2 x squared. So how would you find the moment generating function for this? So that's just going to be what? So mx of t is going to be equal to the integral from minus infinity to infinity, because that's the domain of a standard normal, and then it's going to be x times 1 over the square root of 2 pi times e to the minus 1/2 x squared. You can of course take this constant, factor it out, realize that there's a quadratic in the exponent and a linear out front. Use substitution or something like that to evaluate that integral, and you're just going to be left with e to the 1/2 t squared, and that would be the moment generating function for a standard normal random variable. And fun little exercise, if you do know calculus 1 and derivatives, is that the expected value of this random variable, as we should know, should come out to 0. The second moment is going to come out to something, and maybe you can piece together these puzzle pieces because the variance must be equal to 1, right? So if the variance is equal to the second moment minus the mean squared, that means this must be equal to 1 as well, right? Because variance is equal to second moment minus the mean squared. So that means the second moment must be equal to 1 in this case, right? So fun little exercise there. And maybe you should try and find maybe a closed formula for the nth moment of a standard normal random variable. Lots of little exercises that you could do here, but I'll stop with that. Now, let us just mention a couple other important properties that you may want to know in case you want to dive more deeper into the theory of moment generating functions. Another piece of machinery that is very, very useful in studying random variables is what is known as the characteristic function of a random variable, which we usually abbreviate by Greek letter phi sub x of t. So this is defined to be equal to the expected value of a slightly different random variable, but it's going to be e to the it capital X, where I is defined to be equal to the square root of -1. So if you played with complex numbers a little bit, or maybe even some complex analysis, you should have recognized I in a variety of places. So definitely the definition of a characteristic function and a moment generating function are very close to each other. So is it possible that we can tie these two things together? And the answer is of course going to be yes. So if we evaluate the characteristic function at minus it, that's just going to be equal to the moment generating function evaluated at t. Similarly speaking, this is going to be true if and only if the characteristic function evaluated at t is equal to the moment generating function evaluated at minus it. So those are very interesting, very easy to prove properties that sort of connect the characteristic function and the moment generating function of a random variable. So let's just do a very basic example of how to create the characteristic function for a random variable. For example, let's consider the moment generating function for a standard normal random variable. So mx of t is going to be equal to e to the t squared for a standard normal RV. So what would be the characteristic function of a standard normal random variable? So that's going to be equal to, so we're just going to be evaluating the moment generating function at minus it. So that's going to be equal to e to the minus it, the quantity squared. So what is minus it squared? So that's going to be equal to e to the minus it times minus it. So that's going to be equal to e to the I squared t squared. But if I is equal to the square root of -1, that means I squared is equal to -1. That means the characteristic function for a standard normal random variable is just e to the minus t squared. Right? Very, very similar. Doesn't have any complex numbers, but it gives you this function. This function is very, very important for proving a very, very important theorem that we're going to look into a little bit later and has a lot of consequences in the realm of hypothesis testing. But we'll leave that for later. Let's just give a couple more properties that you may want to use in case you want to play with some theorems. Right? So some special properties that you may want to just be aware of at least. Because we've studied a lot of variables, x for example, log, normal, gamma, exponential, and so on, but we haven't really dove into the interactions with variables, especially if they're dependent, right? So if x and y are independent random variables, then the moment generating function of the sum of these random variables is actually going to be equal to the product of their moment generating functions. Now this might seem weird, like maybe you would think that the sum of the moment generating function of the sum is equal to the sum of the moment generating functions. Actually, that's not the case, but if you're familiar with a little bit of abstract algebra and isomorphisms, this should not come as a surprise to you. Another property that comes up, if C is a real number and we take a real number and multiply it by a random variable, how does that change the moments? So the moment generating function of C times a random variable is actually just going to be equal to the moment generating function of the original random variable evaluated at C times t. So if we multiply a random variable by a constant, what we can technically do is just multiply all of the values by the constant and then find the moments of it. So that's a very trivial property that should be obvious for the arithmetic mean especially. Now, let us assume that the moment generating functions for two random variables are equal to one another, and let's assume that this is true for all t in the set of reals for which this expression is defined. Then one should be able to prove that the cumulative density functions for these random variables are going to be equal to one another, right? So therefore, up to some certain degree, if the moments are all equal to each other, then the cumulative densities are equal to each other. That doesn't imply that the PMS or the PDFs are equal to each other exactly, but the cumulative density functions are going to be equal to each other up to some particular point. And this is actually how you can construct probability density functions if you know the moments or some of the moments of the random variables. Then you can maybe approximate things if you want to. And one last thing that you may want to be aware of, but the moment generating function evaluated at t is always greater than or equal to e to the expected value of that random variable times t, regardless of the value of t. So this will give you a bound on your moment generating functions. You might be able to introduce derivatives and stuff here, but I won't get into the consequences of this particular theorem. But if you are in the theoretical realm, these definitely will be useful for you. Anyway, that's just a brief introduction into moment generating functions, MGFs, and characteristic functions for random variables. This discussion definitely can go on a lot deeper, but for an introductory discussion, just exposure to it and familiarity with it, and some of the things that it can actually do for you, very, very beneficial, especially if you want to go into the research world of modeling random variables, either from the theoretical or empirical perspective. Anyway, I hope you enjoyed, and I'll see you in the next video. Take care.